Hello, my name is Jonathan Home. It's a pleasure to be here with you today. I hope you're enjoying your workshop, and I'm very sorry I couldn't join you there, but this is the first time I tried to give a talk on my own in my house. Let's see how well it goes. So I want to describe to you work we've been doing at HHRI in the last few years towards trying to scale up trapped ion quantum computing. And the chip that you see in front of you, and I'm outlining with my cursor, is a part of that flow. It's a special chip in one regard. In some sense, it's a standard ion trap chip. You can see electrical connections, wire bonds connecting to a gold surface, and ions are trapped about 50 microns above this gold surface. What's rather unique about this chip and focused on scaling up these systems is the stuff that you see over here. There's actually a bundle here of 8 fibers coming onto the chip, which get butt coupled into the side of this chip, which can then run the light through to couplers, which outcouple light locally close to the ions so that they can be controlled locally. And that's a key step towards trying to scale up trapped ion systems from what we have today, which is tens or so of qubits, to thinking about systems of millions of qubits, which we might have to go to in the longer term. So that's just a picture to get you started. I first thank all of the people that fund our work, of course, and that's a very important part of supporting our research. So let me put a little bit the context for why we're thinking so much about scaling. So here's a diagram which probably you're familiar with. It's the notion that if I take a problem that's, say, specified by a number of bits and I make it larger, then a classical computer for some problems has an exponential dependence, and that's what I give by this straight line. You can imagine an exponential axis on this axis here on the size of the problem. And that quickly leads to a situation for some problems that classical computers just run out of time and resources required to do these problems. And the beginning of quantum computing, of course, is the fact that quantum computers scale differently, right? But to really access the power of that scaling, actually, what you need to do is to build a rather large quantum computer to get as large as possible a gap between what a classical computer can do. These are some of the most wonderful devices we have in the world today, I think, classical supercomputers and the quantum computers. So that would just be the case if we just had quantum computers. We think probably with around 1,000 qubits, then quantum computers could do algorithms of practical interest, which would be interesting, which we can't do on classical computers. And some of those algorithms are things like molecular structure. So this was analyzed by my colleague at the time at ETH. He's now at Microsoft, and co-workers working at ETH. And they estimated actually that when you look at some molecule like this, which is one that bacteria use for nitrogen fixation and is used then in photosynthesis, you see that around 1 million qubits are needed to perform this algorithm, and about 10 to the 17 gates. And why is the difference between my 1,000 and 1 million? Basically, all of the rest is about the fact that all the devices we will ever build in quantum computing are faulty. So what we need to do, and what they'll spend most of their time doing, is correcting errors. And that leads to a massive overhead in the number of bits that are required, the qubits that are required to build quantum computers. So let me just give you a couple of ideas about what error correction involves and why it gives this large overhead. So the main observation really in error correction is that errors somehow, due to physics, they mainly act locally. Most sources of noise and things act in a region of space, in a close region of space, and so they affect a few qubits in a certain area. Yeah. And the solution given by quantum error correction is first, not to store information locally. So delocalize information so that it sits distributed across a number of qubits. And then to repeatedly, in a very subtle way, go and check for errors and correct any errors that you see before they have time to accumulate so many that the amount of error causes some corruption of this delocalized information. And so the kind of measurements that have to go on there, they're not to measure individual bits. In general, that would collapse your quantum computer into one state and make it completely useless, if you like. But they go around and they keep examining the correlations between various qubits in an array. Yeah. And so the smallest instances of codes that you can think of that can correct errors are 7. So you can imagine that there's a qubit at every node of this code. And in this case, you have to do these 4-point correlations to check for errors. And you do that on each of these blocks of 4 that are surrounding these areas. But in fact, if you think about a real error correction code on a computer, 7 is a minimal instance, but it's actually then quite susceptible to errors. So in fact, what you want to do is encode information on this entire landscape sitting in the background of qubits, which then gives much bigger delocalization of information and allows you to still compute. And so you can do some rough estimates. This is sort of taken from a paper a few years ago by Austin Fowler and co-workers of what you need if you want to do something like Shor's algorithm, which is a cryptography breaking algorithm. And you can go and stick in some gate errors that you might think for a physical system might be achievable. I would say these are very ambitious. These are better than anyone's ever done. And what you find is that if you use ions as your physical qubit system, you would need about 2,700 ions per logical qubit if you could achieve error rates better than we can achieve today. Yeah, and this is the factor of 1,000 overhead between my original statement that interesting things could be done with 1,000 qubits and the statement that actually it needs about 1 million. Yeah, so it's the error correction which is pushing the scaling of quantum computers even before we get to interesting problems. So where does that leave my particular technology that I choose to pursue, which is trapped ion quantum computing? So the state of the art in trapped ion quantum computing in terms of qubit numbers is very often realized by devices in which basically you take a trapping potential and you put all of the ions of interest into that trapping potential. And then you engineer your optics so that you can shine light on individual ions in this chain. And because this chain all moves together, by imparting forces with laser beams and shining light on, for instance, this ion and this ion, you can make the whole chain move conditional on the internal states of these two ions. And if that's different, depending on the internal states, then that's enough to introduce a 2-qubit quantum gate between the two. So the problem comes down to, can you stably trap long strings of ions, and can you provide the optical fields without any crosstalk? And this is where we stand today. And this has been very successful. There's been some beautiful experiments with up to 50 qubits, algorithms even with running up to 20 qubits or so, and even in the last few years, basic error correction gadgets demonstrated in this approach. And that's actually led to people even starting companies, because there's interest in qubit systems above 50 qubits. Nobody really knows what they can do. And so there's a possibility there that there's some application hidden that we haven't seen before, though I'm rather skeptical that that exists. So that's where we are today. But if we think about trying to scale up to 1 million qubits, that's an extremely hard challenge. And so the main approaches that we think about are to modularize the trapped ion quantum computer. And the modularization we think of in 2 ways. So the first way we think of doing it is actually by breaking up these long strings of ions into many different regions of an array of ion traps. So here, instead of just having a single zone where ions can be trapped, you can see in this cartoon, because of the segmented electrodes here, which allow us to create trapping potentials for here 5 ions, here 1 ion, another ion sitting over here. And a key component of this is being able to reconfigure these strings of ions by shuttling ions around inside this processor. Now, this is harder than up here because, for instance, you have to control all of these different electrodes and you have to control multiple optical fields if you really want to take advantage of this approach. Another way of modularizing is to provide photonic links. So make ions emit photons and mix those on beam splitters. And these can be fed through interconnects, which are maybe switch-based, which can allow you to distribute entanglement between pairs of ions in different units, separated by meters, if you like. Now, the problem with this, or the challenge in this, is that it's probabilistic, right? So you don't get always an entangled pair, right? But it's also fairly, at the moment, slow, and that's because the ion-photon interface is fairly poor. You lose a lot of the photons that you try to connect. So this is a little bit less immature. Nevertheless, I think probably both of these approaches together will be required to really scale up to a very large system. So today I'm going to focus primarily on the quantum CCD architecture. And when we think about the quantum CCD architecture, and I've alluded to this already, one of the major challenges, one of the great advantages of this architecture is actually that you might be able to control many zones of this array in parallel and do gates on small numbers of ions. That means you can usually get very high quality because these are very clean systems, but you can do it in parallel in multiple zones. And we've been trying to do that sort of thing in our lab for many years, and you see a setup that we used for this. But one big challenge we had is that all of our light that we were using came in free space through this vacuum can. And while my students were fairly happy to line up laser beams for actually 2 species of ion on one zone of the processor, lining it up on 2 and having really good control of both of those sets has been really something that I haven't had the heart to persuade anyone to do. It's hard. There's a lot of work to be done, and this starts to become very hard. And that's because the technology is just the wrong technology for doing this. We're trying to do it in free space. And in fact, we should go to approaches which can deliver parallel sources of light. So what we would like in the end, of course, is that we take a laser. We can split up its light. Maybe the laser is extremely stable, exactly what we want. We can pass it through a bunch of modulators to modulate the light, and then actually pass it straight into the ion trap chip and deliver the light directly to the ions exactly where they sit. And that's exactly what we've realized, which I'm going to describe in the first half of this talk. In fact, this is the picture of the trap that you saw originally. It sits inside a 4 Kelvin chamber, so it's in a cryostat, and inside an outer vacuum system. Yeah. Now, we're not the first to have done this. This approach was pioneered by the MIT and Lincoln Labs group. So Karan Mehta with them was a PhD student who really pioneered this in this experiment here. And that was followed up in some very nice work that the same group has done, where they showed that in the early work, there was really just one wavelength of light, 674 nanometer light, which went to the ion. But in the more recent work, they've been able to deliver also near ultraviolet light, so about 420 nanometers or so to the ions. Now, a big challenge in all of this work from MIT was that there's a very large loss going from about the input of the chip here to the ion, a 33 dB loss, which is more than a factor of 1,000. That's quite large. So that was one of the things that we wanted to overcome. We were fortunate that Karan Mehta came for a postdoc in our group, and this is really where all the work on our side on integrated photonics has stemmed from. So what do these chips look like, and why can they be used to deliver light? So they look like this. This is a stack up of the chip. You'll see on the top is gold, and that's the electrodes of the trap, and the ion sits about 50 microns above the surface. This whole stack is about 10 microns thick. You see also a platinum ground plane in this first generation of traps, but below it is really the new stuff. That's the silicon nitride waveguides, high quality silicon nitride waveguides, which guide light like wires inside the chip. And then when we get to the place where we want to deliver light out of the chip, we have a grating which diffracts the light and focuses it above the surface. This is all done in a fairly standard foundry, on a silicon substrate. Okay, so and one thing to note is actually that this grating doesn't just take light out of the chip directly, but also reflects some light off this bottom surface in order to deliver it. So as I said, we use a commercial foundry, a photonics foundry called Lionix International. They have a nice ability, which is very useful for us in getting high throughput of light. And that is, they have the possibility to do these 2 layers of silicon nitride. And when they use thick silicon nitride, what that means is the mode of the optical mode is extremely well confined, and that's good for routing wires, optical wires on the chip with low loss. And then, but what we want to do is to match the optical fibers that we'll butt couple to the chip. And at that point, this mode is too small. It doesn't match the mode of an optical fiber. So what we do is we then, at that point, have the mode confined in a thin silicon nitride layer. And this means that this mode is much larger. You can see that from the plot. And that's much better suited for fiber matching rather than the routing purpose that we have for this first part. The gratings, how do they look? They're written by E-beam lithography. So you'll see one of these silicon nitride wires coming in here, essentially, or waveguides, delivering light. So there's a taper here, which adiabatically expands the optical mode. And then a 300 nanometer period E-beam grating, which is curved here to allow the light to focus out of the chip and focus at the position of the ion. And it's carefully designed to do that. So here's, again, the picture of the chip. You've seen this already. Here is a zoom in of the central region. You see 3 blue dots here. The 3 blue dots are the positions above which the ion is actually trapped. You see some openings here which have the gratings in. You may see some larger gratings sitting here. Those are the ones used for tightly focused 729 nanometer light. And there are some gratings here which are used for less tightly focused. We don't need as much power, 854 and 866 nanometer light. Now, as I said, one of the key challenges and one of the things we wanted to do was to make sure that we could couple as much light through to the ion as possible. And indeed, Karan's been very successful at doing that. So he's been able to get the fiber to waveguide losses down to a 1.5 dB level, both at 300K where we set it up and also at 7K where we operate the chip. And that's been really useful. It means that our total losses from input of a fiber through to the ion are about 7 dB, and that allows us to get 600 nanosecond pi times, which is much faster than was achievable before. But that really takes us into also a new regime, because what we really like to show is that we can do 2-qubit gates. And 2-qubit gates are slower than the typical single-qubit gates because they use the gradient of the light field rather than the gradient of the Rabi frequency of the light field, right? So there's some penalty you pay by trying to transfer momentum from the light field. And so that means you need typically larger power to do 2-qubit gates. But the nice thing is that with the amount of powers that we get, and just with 1.5 milliwatts emitted from the coupler, we're actually able to, this is a trace from, you can see these are 2 ion traces. So the ion is up in this black trace, down in the blue trace, and either up, down, or down, up in the red trace. This is a very classic trace from what we call a Malmo-Sorensen gate. And what you see from the high contrast is that it's fairly high quality, and that we have at the gate time of 65 microseconds, we go from a situation where we started with the ions down, and here we have a superposition of the up, and down states. That's a Bell state, and that's a maximally entangled state. So we can characterize that by an interference experiment, just looking at the coherence between the 0, 0, and 1, 1 states, or if you like, the down, and up states. Here you see the effectively 2-qubit Ramsey fringe that we get from that. And you see that the contrast is very high, well above 99%. And that tells us that our fidelity of our gate is 99.3%. So that's not the best that's ever been produced. I think the best gates today have been 99.93%, so we're a factor of 10 off. But nevertheless, for a first shot in this new technology, we were very happy with this result. And what's nice about it in a sense is that we understand very well all of the sources of errors. We think we're in control of all of those. And in a certain sense also that this was a bare gate. We didn't really work hard at optimizing, having pulse sequences to mitigate any of these errors. But nevertheless, out of the box, we were able to make it work reasonably fast. This is a reasonably quick gate and with a reasonably high fidelity. So we think there's a good path to trying to improve these fidelities. Now, this is just a one shot. We use a single gate to try and get a 2-qubit entangled state. We've also done further experiments where we've actually been trying to show the ability of dissipation to pump into an entangled state. I don't want to say too much about that. The scheme is based on symmetry. And in that sense, it's quite a good test of our integrated optics. So let me describe this scheme. Here you see, written in a slightly strange way, the ground states of the calcium ion. So up, down. And here's the singlet state. So up, down, minus, down, up. And here's the triplet state, up, down, plus, down, up. Now, what we do is we turn on a Malmo-Sorensen gate field, which then performs a collective excitation from down to an excited state, an extra state, if you like. And what that does is it just empties this state once in a while, okay? The other thing we do is we turn on a microwave field, which just drives the ground state qubit. And what it does is it's a symmetric drive. It equally drives the 2 ions. And what that does is to connect all the symmetric subspace of this system, but doesn't connect to the singlet state at all, as long as the symmetry is met. Yeah. So what we find with that, if we put that all together and we have some optical pumping from the excited state that decays into the ground state, is that we can pump into a singlet state. And here's some curves. We start from various different states, and we see that with about a 93% probability, we pump into a singlet state. But as I say, really what I want to focus on today is not that, but the fact that this is very sensitive to symmetry. It's a symmetry-based scheme, so it's very sensitive to uncorrelated errors, even though, and its attractive feature is that it's very robust to correlated errors. Now, it turned out in this particular system with the integrated optics, that enabled us to find various uncorrelated errors, which I think we wouldn't have necessarily spotted. The other thing that it tested was our ability to do many gates in a row. So there's about 32 gates being used in this sequence, anticipative pumping. And we saw various problems that came up by running these extended sequence. So we saw we were limited by frequency drift, motionally heating of spectator modes, not the ones we were using for the gates. And as I said, these asymmetries in the optical field, which we were not expecting at the time. So there's work still to be done on the integrated optics in that respect. So further to that, the other nice thing about the integrated optics is it allows you to make optical fields that you otherwise might find tricky to work with in the lab. And one of those is standing waves, and we're working with that at the moment. So why would we want to use standing waves? So in a traveling wave, what you find is that as the wave washes over the ion, any location where you put the ion experiences both the electric field, but also a half cycle later, it'll get the gradient of the electric field. Yeah. Or let me just say Rabi frequency and gradient of Rabi frequencies for reasons you might see in a moment. Now, in a standing wave, you don't have that. You can spatially isolate whether you have a strong Rabi frequency of a given transition or whether you have a gradient of a Rabi frequency by sitting at nodes or antinodes. Now, the challenge in trapped ions of realizing standing waves is making them phase stable relative to the ion trap. But in the integrated optics approach, what we have is a situation where we're delivering light right from the ion trap. And that means that we can get phase-stable standing waves that propagate from two beams coming out of two opposing gratings and sit, which are focused to sit exactly 50 microns above the surface. Now, it's an interesting standing wave. It actually propagates away from the surface. Yeah, the electric field is in plane, but it's a standing wave in this direction here. And we've been playing around with that. It's got some interesting features. So I won't go through all the details of this. We're driving a quadrupole transition, and different components of field contribute to different Rabi frequencies of different delta MJ changing transitions in the quadrupole transition. So if we look at the carrier, we see three different transitions, and at different positions along the axis of this standing wave, we see different Rabi frequencies on the carrier. Now, on the sideband, we should see Rabi frequencies strong when we have the strongest gradient of the Rabi frequency. And so what you see is that for a sideband, let's compare the black case, or maybe the blue case is easiest. Wherever we get a maximum on the sideband, it's where we've got actually a minimum in the carrier. Yeah, so this is where the maximum gradient of the carrier strength is. That's where we get a maximum of the sideband coupling strength. And we can also look at the AC Stark shifts of our transitions, which are mainly due to dipole transitions. And we can see also that by changing position, we get a different amount of AC Stark shift, because actually at this point here, there's no intensity of the light present. Yeah. And actually, this is a very interesting point if you want to do Molmar-Sorensen gates fast, because there what you want to do is you want to drive sideband transitions. So you want to maximize the strength of this. So you might pick this delta MJ as one transition here, the blue. Yeah. There you see you minimize the carrier, which is actually one of the leading off-resonant terms that causes trouble and limits your speed. But you also limit AC Stark shifts, or minimize AC Stark shifts, which are another component in another basis, which also cause problems in the operation of this gate. So what we're hoping to do in the next months is to have 2 qubits and try and perform gates sitting at these points in order to get a high quality but fast 2-qubit gate. So where are we? We've shown operations in a single zone. We're now starting to add transport. So a simple experiment was just to try and make the ion dark and transport it and repump it with 854 and 866 nanometer light. As a function of the final position, this is very preliminary data, but you see that there's a change in the probability of being in the excited state, depending on this is the 854 time, so the repumping time, and you see that the final position where we finish our waveform tells us how fast we will repump the ion. So we think that the transport is starting to work for us, and we can do that in the current chips. We also have chips that can investigate a key component of this Ccd architecture, which are these junctions, which have been pretty tricky to operate in many experiments so far. But one nice feature of the integrated optics, this is actually just a picture prior to fabrication, is that you can have multiple zones that are all wired up with light. Very easy, don't need to align them. And these can set the wings of this junction, which we have optimized to try and perform high quality transport through the junction. This chip also has this interesting array here with many lines coming into it. So this is actually aiming to have a 5-ion array and have 5 individual beams that heat each of the 5 ions. And we've actually imaged those light fields coming out of the chip, and you see that they're nicely focused at the positions of the ions, and we're looking forward to using such a device soon. So this was the first generation chips we have back from Linux. We've also been designing recently a second generation of chips that are ready for order. And there are a few things we want to fix. The heating rates in these chips are high. We have drifts of electric field when we pulse on these laser fields with a lot of light, and we can't currently use UV wavelengths. So there's a few fixes there. We want to have a conducting layer on the surface to shield charge. We want to introduce these Illumina waveguides to guide UV light. We don't just want to fix things, but we want to explore new things. So we're exploring new grating designs for doing detection, addressing of ions and interesting types of gates that we'd be interested to perform. And we're also looking if we can scale. So what are the challenges to scaling? This chip here, you'll see everywhere you see something, this red dot, is a point where is actually a different zone of this trap. And what we're trying to do here is have a chip which has a 4x4 array of experiment zones with a set of also loading zones sitting at the end here. So that's 20 chips, 20 zones in parallel. And the challenge here will be to operate all of those 20 in parallel, which is a new challenge for us. We usually stare at a single zone and work with that. So this is really thinking about scaling. So where do we see the challenges with all of this? Well, one of the challenges that you see here, and one of our big worries, is the use of radio frequency fields in the chip. And radio frequency fields are an intrinsic part of any of the pull trapping we see today, but they, I think, provide big challenges if we think about scaling. So first up, a reason for that is that if you want an RF null, which is where we like to trap ions for stability and laser control reasons, you'll find it's intrinsically 1D. That's why you see these beautiful long chains of ions are always 1D chains of ions. Yeah. One of the things that we do fairly often is to try and align the RF potential, which is providing 3D confinement or 2D confinement in the radial plane of these ions, and the static potential, which is trying to, which is more usually used for control. Yeah, and that's called micromotion compensation. We're trying to get rid of the driven motion, get back to the RF null line. But that's something that's a common experimental technique being regularly performed during the day. And then if we think about scaling up further, one big problem becomes that RF is being driven through chips, and you get heating of these chips just from the fact that you have dissipation on them. This is not Sandia's probably best chip ever, but what I wanted to just show is this image, which is a thermal image looking at a trap that's being run. Yeah, and you see that there's heat being dissipated from this chip. So it makes you wonder whether there might be better approaches to scaling up ion trapping, even if they weren't the first approaches we took to doing ion trap quantum computing. And that's where we come to another theme of my group, which is today to pursue microfabricated penning traps. And the principal idea there is to take a situation where you have static and radio frequency potentials and replace it by a situation where you have an array of static potentials, each of which traps a single ion, but the 3D confinement is provided by a homogeneous externally applied magnetic field. So no dynamic fields here in order to trap the ions. And there we build upon stuff that's been done for pull traps, where people are thinking about trapping in 2 ion trap sites and bringing them close together such that the ions in these 2 sites couple to each other. And what we noticed was that actually you have an advantage if you do this with static potentials only rather than with RF potentials. And why is that? It's just because when you use a pseudo potential, a this fast time varying potential being averaged down, you weaken your curvature of your potentials. Yeah. So what we noticed was we should be able to get the ions more closely packed with penning traps. Yeah. And what that means is that we think you could have large arrays. This is actually a calculation for an infinite array, where the distance between ions is close, and that means the Coulomb interaction can be large, while the height above the surface is maintained at 30 microns, which means that heating, which is a principal source of error, could be minimized. And we see decent exchange rates even in this sort of infinite lattice type setting. And it encourages us to think that, with a 1 centimeter squared chip with this sort of ion density, you could think about trapping 250,000 ions or so with no RF power dissipation whatsoever. So that's very encouraging. We're not close to that yet. We haven't trapped one, right? But nevertheless, it's an intriguing possibility, which I don't think is feasible with RF traps at all. So what can you think about doing with that? You could think about doing quantum computing. I'll fix on quantum computing, though we also think about quantum simulation. That's all covered in this paper by Shreyans Jain on a fixed lattice. So the idea there is you have a lattice. Here's a square lattice. And when you want to do gates between neighboring ions, you tune two trapping sites locally by tuning their static potentials, and you tune their frequencies to a special point, which the other ones are detuned from. So if we look at the normal modes, when we've done that, we'll see, in fact, there's a very special point which enhances the 0-point motion. I won't talk about that in any detail. And you see there's 1, 2, 3, 4, 5, 6 collective modes of these two ions, which are then well separated from all the other modes. So here's frequencies of modes, and this is the 270 or so modes of this 90-ion system. Yeah. So here, now well isolated, are 6 modes of this, which are the modes of these local ions. And that then allows you to do local gates with no need to couple to the motion of all the other ions. So we've been looking at that, and it looks very encouraging, actually, that you could do a fast gate, 60 microseconds or so, with very reasonable Rabi frequencies, even working in a large array such as this. Yeah, so this hints that it might be possible to work in a fixed lattice like this. But we also think about a movable lattice. In fact, the key to this quantum CCD architecture, as I said, was transport of ions. And one of the challenges in an RF trap is going into 2D, because this RF null is intrinsically one-dimensional, as I said before. And we anticipate challenges, and indeed people find challenges when trying to operate these junctions. But in a penning trap, the 3D confinement is provided by a homogeneous magnetic field. So actually, all you have to do to move ions in 3 dimensions is move their static potentials. And that suddenly frees you up. You can move ions in 2D, you could move them in 3D, and the possibility for reconfiguring the array of ions seems much more flexible here than it is in the RF trap. So we're starting to build an experiment to examine this. The key component that's additional to an RF trap is a superconducting magnet, right, which sits around the ion trap. We built a cryostat system where the vacuum system goes in the core of the cryostat. And one of the problems, which of course the referees pointed out for our paper, was that how do you get the optics and things into the cryostat system? Yeah. So this is what we've realized. This is what we have inside the system. This is the 4K chamber. You see some charcoal getters sitting there, a filter board, which is fed by a bunch of PCB lines. Yeah. And the ion trap sits in this box with an objective, a Schwarzschild objective that sits above it and actually guides light out through this hole at the end here. Now, if we look down on the trap in this case here is not one with integrated waveguides. It's rather one which has just a gold surface, if you like. Then it sits at the center of this little pack. And the stuff you see around here is actually all the optics, because all the laser beams have to come in from the top, coming in from the end of the superconducting magnet. So just a couple of them that I draw their paths. You see one that goes straight across the ion trap, another one that goes zigzag and comes at 45 degrees across the ion trap. But indeed, all of these are aligned. Yeah. And we're trying to trap this system at the moment with great anticipation. We're looking forward to loading it. So in summary, I've told you about how we have demonstrated now 2 qubit gates using integrated optics, and some of the interesting physics that opens up, but also the interesting possibilities for scaling up based on these approaches. I think it's a very nice playground to be working in. And second up, I have alluded to the fact that maybe in future, the key will be not scaling up based on radio frequency traps, but scaling up using penning traps with the corresponding getting rid of this high voltage RF on the chips, which we think will open up possibilities in quantum simulation and quantum computation. And you can read more there in this theory paper. And the experiment is just trying to load ions, supported by the European Research Council. So thanks to them. So with that, I thank my group. This is not just a group working now at ETH Zurich in my professorship, if you like, but also we've established recently a joint institute or a quantum computing hub with ETH Zurich and PSI. And PSI is a particle physics lab used to dealing with larger infrastructure, and we're hoping that that helps us in scaling up ion trap quantum computers. So with that, I also thank you for your attention, and I hope you enjoyed this talk. And feel free to contact me by email if you have any questions to follow up on this talk.